Thank you. A few people have asked me this week what this talk's about, and it's not a masterclass in writing compact code or anything like that. It's more of a kind of a wander through my childhood. But perhaps the best way to sum it up is this quote from my school report when I was 14 years old, which was written by my geography teacher. So, I was born in 1971, so I'm a similar age to Unix. I grew up in England, and about the time I started to use computers was about the same time that 8-bit micros really started to come into their own. And this is my first computer. It's not my actual first computer. This is from the Science Museum in London. So it's now a museum piece. It has a Z80 processor, which is kind of where the name came from. It was first released in 1980, which I guess also partly explains the name. It was very much built for a price. It was the first real computer for under £100 in the UK. Sinclair also made something called an MK14 before this, which was also under £100. But that didn't really have a full keyboard. It had like a 20-button keyboard and a hex display, whereas this had, you can't really see in this photo, but it's a QWERTY keyboard, or a fairly minimal one, and you could plug just a TV into the back.
It's sold here in Australia.
Okay.
And the follow-up is ZX81 next year.
Right, yeah. I should have checked that, I suppose. They were quite kind of crudely made. There was an expansion connector on the back, which was just raw PCB sticking out. And although it might look like it has ventilation slots, they're simply painted on the case. And as a result, the things overheat quite badly. And the expansion connector caused problems because, for example, you could connect a bigger RAM pack onto the back because they only came with 1 kilobyte. And when you typed, the RAM pack would like wobble and eventually fall off, and your computer would reset itself. So my family bought one of these in, I think it might have been either late 1980 or early 1981. It was about the same time as the ZX81 had come out, and in fact we bought it second hand from a friend of my father's. And I was hooked right away. It has some interesting features. It only has 1K of memory, and that's shared between the video memory and the memory you type your program into. So as your program gets longer, your screen gets shorter. So if you write a sufficiently long program, it can only use 1 line of screen. It has the whole kind of operating system fits into a 4K ROM inside. And in order to make that easier, the keys are quite complex. They have various different modes. And so if you want to type print, you want to type print, you have to be on the right mode, and you press the P key, and print appears. So this was sold in the manual as a feature to save typing, but in reality, it's a clever way to get the user to do the tokenization for the operating system, so they don't have to have code in there to do it. So that was kind of an introduction to the idea of selling drawbacks as features. The other thing about the screen was that it was a CPU that would send the data to the video circuitry. So if it was running code, it couldn't display pictures. So every time you ran something, the screen would go black, and then it would finish, wait for key input, and it would show you the results. So its successor was the ZX81. The ZX81 was very similar in hardware to the ZX80, except that they'd replaced most of the chips inside it with one custom, what they call the ULA, an uncommitted logic array. And this machine only has 4 chips inside it, which is probably an early example of integrating everything for chips. It's very common now. I mean, ARM chips are commonly integrated into a much bigger circuit. It includes the rest of the circuitry for the device. You can actually see the tokens better in this one.
If you actually spelled out PLOT, for example, that wouldn't work because it's actually then 4 characters which are not the plot token.
And in fact, you can't type plot because it's in keyword mode at that point. This means, in fact, that it's very hard to type in a program that has syntax errors in. The other feature it's introduced, which was a bit revolutionary, was that it could actually show you a picture and compute at the same time. They added a non-maskable interrupt generator so that it could run very slowly, and it would spend most of its time sending data to the screen, but also could execute code at the same time. And someone very cunning managed to write something for ZX80 that did the same, but on a user interrupt. And you could actually upgrade, because the hardware is very similar apart from this non-maskable interrupt generator, you could upgrade an 80 to an 81 by sticking a new ROM chip in and a keyboard overlay. And we actually did that to mine. And all you got was everything except the slow mode. The ZX81 had an 8K ROM, and it added floating point support. But the drawback was this meant that numeric constants now took 7 bytes. I'm not quite sure why it was 7. It was 5 for the actual floating point representation. It had a pretty wide floating point representation for the time. I mean, the IEEE float is 4 bytes, so this had 5 bytes, so it was actually better than that. I guess there were 2 bytes in front which said this is a number coming up. So if you said x equals 1, that would take up quite a lot of space. And so people come up with elaborate ways to avoid this. So instead of writing 0, you'd write not pi, which took up 2 bytes instead of 7, saving you 5 bytes. And similarly, you could write sn pi instead of 1, so that's the absolute magnitude of it. The integer value of pi, cos of pi. The integer value of the exponent of the sine of pi. Sine pi minus int pi. And int square root of the exponent of pi. And the other thing you could do is if there was a constant that you wanted a lot, you would assign it to a variable, because you only need to use it about 3 times before you've made back the cost of assigning it somewhere. So, some lessons learned here was a trade-off between size and speed. In fact, there are 2 trade-offs between size and speed going on here. The operating system has decided that it's better to store the constant using more space because it can read it more quickly. And then the user has decided that they don't like that. So what they're going to do is they're going to make the program less readable but faster. But smaller but slower. So it's a kind of interesting. The user trying to undo what the operating system's decided for them. And shaving bytes really can still matter. I spotted a slight, slightly not as packed as it could have been packing in the keys used by Xapian. And by shaving 2 bits on average off the key size, it didn't really seem like a very important thing at the time. As I was implementing, I just thought, it'll save a bit of space, it's neater to do it this way. But it gave a 2.5% reduction in the total database size. So my next computer was a BBC Model A. These were built as part of the BBC Computer Literacy Project in the UK. And the BBC decided that they wanted to try and run a project to get people more into computers. So they came up with a spec for what they wanted, and they sent this around to the various micro manufacturers, and almost all of them wanted to take part. And Sinclair was very upset he didn't get it, but in fact Acorn did with this machine, which was a successor to their Atom. And it basically met or exceeded all of the specs that the BBC were after, which nobody else who'd applied had. This had a 2 MHz 6502 CPU, which is nominally slower than the 3.25 Z80 that the X80 had, but because they actually put video circuitry into this, it was effectively quite a bit faster. I got the Model A, which was a 16K RAM model. There's also a Model B, which is 32K, and you could upgrade between the two. It's said by many people the 6502 CPU is a bit RISC-like. I think mostly it doesn't have any instructions. But there's a certain symmetry to it. It has an accumulator register in X and Y, and X and Y you can treat, in most cases, the same as each other. Whereas the 6502 has a kind of sprawling mass of registers which you can use in different ways depending which ones they are. So it was kind of a bit more limited, but a bit easier to kind of program for in some ways. And these machines were very popular in education. The successor to this, some years later, this came out when I was in the 6th form. This is the Acorn Archimedes. This is actually a later model machine. The earlier models were a kind of a desktop box and a separate keyboard. For this, Acorn designed their own CPU, the ARM, which you may have heard of. It's a 32-bit CPU, it's a RISC CPU. It's somewhat inspired by a 6502 in many ways. I mean, if you're a 6502 program, you got one of these. It certainly wasn't totally unfamiliar. ARM, in fact, originally stood for Acorn RISC Machine, but it was later spun off as a separate company and rebadged as Advanced RISC Machines, and the parent company, Acorn, no longer exists, really. The CPUs in these around 8 megahertz, which, because it's a 32-bit CPU, that's actually quite a bit faster. It was probably one of the fastest machines of its time. So I got one of these about the time I went to university, where I read mathematics. This is a quote from Tom Lehrer, who's heard of Tom Lehrer? Okay, he sings a lot of comedy songs, which you may have heard but not realised they're by him, including one with all the names of all the chemical elements in it. He's actually a mathematician by training, and I think he lectures at Harvard or somewhere like that. But mathematicians, they can be a bit of a funny breed. So my third year at university, I was on K Staircase in Hewells Court. You'd often get people coming around asking where Wewells Court was. There was Martin Hollis, David Moore and myself. We were all on the same staircase on different floors. And we were all reading mathematics, so we knew each other quite well. David was in fact my supervision partner. And the room I was in on this staircase was in fact one which was formerly occupied by the philosopher Wittgenstein. So this is what we came up with. It's a one-line Tetris game. There was a bit of a trend for writing one-line games as a kind of way to entertain yourself. Most of them were pretty, the explanation had to tell you what the game was. So they'd say, this is a car racing game, and you see some stars and equal signs going on the screen in a sort of wiggly line. What we set out to do was to write something that was actually a recognisable existing game. And we wanted something that was probably possible, was going to be quite challenging. And I think it was Martin suggested Tetris. Martin and Dave did most of the work on this one. I suggested various ideas, but they did most of the grunt work of making it fit. And it was kind of written as a 1200 byte program and then made 4 times smaller.
What's the benefit of the if 0 else if A equals 0? If 0 is always false, isn't it?
Well, because it's a one-line program.
Yes.
So what am I right?
No, it's not. It's you need a way to join flows of control back together, and there's a kind of a bug or a quirk in the way that it parses to find an else. So it goes to the first else it finds. So the if 0 else construct, basically it's joining together the if and the else there earlier on.
Use your shadow.
I was trying to, but it doesn't go. Anyway, David actually wrote a very good explanation of kind of every byte in the program, which is online. So I don't really have the time to explain everything in here. I've picked out a few bits to show you now, but if you want to see it in its full gory details, you can go and look at that. In his explanation, David says the code speaks for itself, even if what it has to say isn't necessarily very nice. So, wrong keyboard. But one interesting thing about this is probably the first one-line program to have a subroutine in it, which took a while to work out how to achieve this. So the first thing this program does is to assign D to itself, which seems like a bit of a waste of effort, but there's a kind of an interesting little bug in this implies almost every interesting little bug in the basic interpreter. A variable has to exist for you to use it, except that when you assign a variable, if the variable doesn't exist, it creates a slot for it before it evaluates the right-hand side to find the value to assign. So if you assign the value in terms of itself, you get 0 for the value. And I actually remember when I first discovered this, it was in a chemistry lesson in the 6th form, and the chemistry master was using either BBC or an Archimedes. They had essentially the same basic interpreter. And he'd written a program to do something. I was looking at it and I thought, that's not going to work, because he has to assign this variable. And when he ran it, and I went, ooh. And I don't remember at all anything else in the chemistry lesson except that one thing. And that one thing quite came in handy. So the trick here is that when the program's first run, D gets set to 0, and then if D, that's not true, so we then go to the else and execute the rest of the program. Then, when we want to call a subroutine, we say go sub false, which I'll explain in a moment. And at that point, D now has a non-zero value, so we now execute the if statement, which does VDUD sends D to the output stream as a byte, and then reads a point on the screen, pos and V pos the cursor position. So to say when using variables, the program uses the cursor position to be the position of a brick. So that basically reads the point where the brick is about to be drawn to see if there's anything there, and then it returns. The reason we use go sub false is that BBC Basic tokenizes line numbers into 4 bytes. And the reason it uses 4 bytes is so that it can only use ASCII values for them, so it can scan forward for like an else or something like that without having to worry about line numbers. False evaluates to 0 on this machine, well, most machines I guess. Although interestingly true is -1. So essentially it says go sub 0, but it only takes 1 byte for the line number rather than 4, so it saves us 3 bytes each time.
You've got your use of -1 there in your for loop as well, for r equals true to 1.
Yeah, indeed. There's also some tricks to arrange the code so that you can't actually type this program in as such. You have to type it in longer, and then you run a little program that goes through and pokes the bytes in the program to remove the spaces and join the lines together, that was a kind of rule which other one-line programs had used before us, so we felt that was fair game. But you have to be a little bit careful to arrange such when you remove the spaces you don't produce something which then parses differently. This magic incantation here is actually encoding the block shapes. So there's a hex, understanding produces the hex constant. So this constant here encodes all of the brick shapes. And it draws them in a kind of a petal-shaped pattern, which can then be rotated around, and there's some magic to move the cursor around in that pattern in there somewhere. So after we completed this goal, I started working with on my own a bit later. I got a bit obsessed by it, and I managed to shave off a lot more bytes and to add some extra features. So, for example, this version, it has scoring. Each time you drop a block, it adds on the vertical position of the score, and then prints that in the top left of the screen. And you'll see the trick of not initializing the variable, just slowly in terms of itself. On the Archimedes, BBC Basic has a plus equals operator, but plus equals doesn't have this flaw. It insists the variable exists beforehand, so we can't use that and save a byte. This is an example of using the same code to do 2 different purposes. So by rearranging the code around it, you can factor out some common code here. What this loop does is at the start of the game, it makes the screen white and then clears all the lines off the screen to produce the box shape we're playing in. And the same code is used to clear lines that are completed. I won't bother explaining how that works. You can see Dave's explanation if you want to. And finally, this random Z at the end, that's the end of game message. One of the possible syntax errors in BBC Basic is mistake, which is what you get for just doing that. And because this is on line 0 is kind of special, and if you type commands in immediate mode, the line number for errors comes up as 0, and the interpreter doesn't say at line whatever if it's 0. So we use that to do an end of game message in essentially 2 bytes, the colon and the Z. So I'm going to do a little demo of this game now, just to show you that it really does work. The emulator is a little bit cranky, so I can't get it to fill the screen. And it took some doing to put it run at the right speed. I basically had to compile it with both optimization off and tell GCC to profile it, which makes sense. And also I tweaked the constant because it's going to be quite hard to play this because I'm going to have to look. I don't have this mirrored on my own screen. So this is just the power on self-test mode as it flashes through various colours. And then sadly shrinks to a much smaller window. Anyone remember that? Okay, so this is RPC-MU. So it emulates a RISC PC, which is a later model Archimedes. Okay, so oops. That's the program. If I run it, ready? So it's clearing the screen. And now you'll see how much I suck at Tetris. So I'm going to get to clear a line so you can see that working. I think it might be. You wouldn't believe how hard to display Tetris behind you. So anyway, I'll just get it to there. It is. So for three things I'd kind of like you to take away from this talk. The first is geography teachers are sarcastic but probably insightful. The second is that the most interesting things really get done when you should be doing something else. And the third is that tinkerability, I'm calling it. From this era, the 8-bit era computers were very kind of easy to fiddle with and to play with, and they weren't open source, but because the operating systems were just written in assembler, you could just disassemble them and essentially get pretty much the source code. I mean, you wouldn't have the labels and the comments, but you could at least poke around and see what was going on. A modern closed-source operating system will be written in C or C++ or some other compiled language, and it's very hard to kind of get back what it's written in. Open source gives you that now. These computers, they often came as kits, so for £20 less you could buy a ZX80, I think it was, and you could build it yourself, and if you're really lucky it would work. But there was a kind of, the user was more involved in the kind of how things worked. They quite often ship with technical schematics. If you look in the ZX80 manual, it'll tell you all the byte codes the basic uses, and I think they even came with circuit diagrams. Certainly you can get circuit diagrams for a BBC Micro quite easily.
And for the Micro being Australia, which was an early Australian computer, they published the entire circuit diagrams in the magazine Review when it first came out. Right.
I mean, I actually bought an alarm clock in about this era, which still works and I'm still using, and that came with technical schematics for an alarm clock. It's very different today. But today, I think open source and open hardware offer these same things. I think if I was growing up today without open source and open hardware being available, I probably wouldn't have ended up in the career I've ended up in. So I think they offer a lot of hope for future generations. That's basically all I've got to say today. So thank you.
Is that the entire program in the Q code?
No, that's just the URL to the website to tell you more.
Could have given us that as well.
So I should have tried to code as a Q code to see if the QR code still works. I do like there's actually Tetris blocks in QR code.
That just means you've been playing for too long.
This is what my Tetris games tend to do. So I have any questions anyway? Sure? Yep.
Have you ever played any or gone in any world golf competitions?
No, but it's obviously in a similar kind of intellectual vein.
Might be best if you don't.
For the sake of me getting anything done anyway. Yep.
You don't start by writing a program like that. You start by seeing, some of the tricks and integrating them into your own code, and then seeing further along.
I think that we actually kind of discovered those tricks as we went along. I don't think there were one-line games before, but they weren't really quite as they use little tricks, but that's the culmination. Lots of little tricks all piled on top of each other, all of which interact, which makes it very hard to actually write. If you look at the website, Dave's explanation, he has a lot of the old versions of the original thing as it becomes shorter and shorter and shorter, and then finally fits in one line. And if you compare the first version with the final version, there is almost nothing in common. Yeah. So it's along the way between that first version and that final version, we learned a lot of ideas and tricks. So an original version of it encoded the bricks simply by storing them in a rem statement at the end of the program and then peeking bytes out of that. And then we realised that we could miss off a rem and save a byte, and then when the program ran into that code, it would just say mistakes. That gave us the end of game message for free. So the idea of the end of game message as just being an error message came from that original version and then got reused. So a lot of these ideas got kind of reused and folded back in and distorted.
Do you see there's that same kind of opportunity to learn and find new interesting things in modern code though?
I think probably less so. I mean, a one-line program kind of makes more sense on an 8-bit machine. And I mean, the way we were writing this, in fact, on the 32-bit Archimedes, one of the earlier versions did run on the BBC Micro. My final version certainly doesn't, because it uses a sys command, which is an extension of the basic in the Archimedes. And the main problem for the BBC version is finding a suitable screen mode, because you really want one with at least 8 colours. I don't think there's a square pixel 8 colour mode on the BBC. I think you have to have either 4 colours or non-square pixels.
You still have, for example, the OLPC, which kids can learn how to code it first in Python, and later on they can get right into the others if they want to.
Yes, I've not played much with the old BBC, so I don't really know if it kind of offers this much fiddleability.
But kids get root on their own machine if they want.
So that's quite cool, really.
Because I guess my other observation.
Sorry. No, you finish.
Go ahead.
I was just going to say, have you been following the Raspberry Pi project at all?
Yes, I have.
I'm
quite keen to buy one with it.
Yes, that's really took me back to...
And interestingly, they have a Model A and a Model B.
Yes.
Yep.
Some of the same people are involved, I think.
Yes.
Model B,
the guy who wrote Elite for the BBC Micro.
David Brabham.
Yeah, I think he's involved
Yeah.
with a non-profit. It's great.
So was... Yep.
Is this the way we can learn from like compact code?
There's certainly advantages to compact code. I mean, I think there were 6 bugs in the first realism, and my code actually fixes 2 of them, so it has 4. But you know which line all those 4 bugs are in. But I mean, that's kind of a joke, but compact code is kind of easier to understand, at least to some extent. I mean, there are some ludicrous tricks in there, but before you get to that limit, at least, there's a certain simplicity and elegance to it. The data structure for representing the bricks, for example, I mean, although it's compacted down to a ludicrous extent, it's actually quite an elegant way of representing them. They're stored in a kind of a bitmap that is shifted along, and you draw it by simply rotating it.
It's a good mental discipline, I think, for any code that needs to be scalable, because as you pointed out with the Xapian example, a lot of these things people think, we have gigabytes of RAM these days, who cares? But anytime you need to scale things up massively by several orders of magnitude, if you have that mental discipline of shaving a few bits off, suddenly it matters when you scale it up several orders of magnitude.
And although you might have gigabytes and gigabytes of memory, the cache sizes are smaller than that.
Yeah.
And if you fit in cache, you suddenly go a lot faster.
Yep.
Yep.
And it's really, really easy when you start talking about processing and big web pages and things like that to start.
You did those scales suddenly,
If you have a look at Google's homepage and have a look at the small amount of stuff that it sends you, it's nothing to do with processing time, it's just purely to do with network.
Because suddenly you need to send it to tens of millions of people, that's a very big number of orders of magnitude.
And the way they sort of images into the one.
Yep.
Your original programs are relying on quotes and bugs. Do you find that the emulators are then fixing the people that write the emulators and fixing those quirks and breaking your program?
No, because at least in the emulator I'm using here, you have to get hold of the original ROMs for the machine and install it. So the emulator is open source, but the ROMs aren't. So it is literally, it's an emulation. There is actually an implementation of BBC Basic that's native, and that doesn't work with it. I believe I've spoken to the author in the past by email, and he said he actually used it as a torture test, and he regarded it running with it as a sort of sign that he was doing it right. But I was trying to find a way I could run it today to show to people, and that seemed a more obvious way, and it didn't work. Any other questions? Okay, well, it's just after 3, so let's wrap up.
Thanks,